Okay, now we have the tools that we need to find the exact area under a curve. Right, and I'm back to the same one we've been using, right, that we were talking about before. And instead of doing an approximation, I want to find the exact area. Okay, I've got our Riemann sum formula here. What I'm going to do, right, I'm going to, instead of dividing this into a specific number of intervals, like we did 1, 2, and 4, I think, in the first lecture in this chapter, I'm going to do this using a variable. I'm going to divide it into n intervals, right? So what does that mean? Well, what is delta x in our Riemann sum here? Well, delta x is the length of the interval, that's still 4, divided by the number of sections we're going to divide it into. So that's 4 divided by n. And to do this, I'm going to use the right endpoints of the intervals for my xi or xn star. So xn star will be the right endpoint. Okay, so how can we get those? Well, let's do this with a number again, just so you can, because I think it's easier if we do this with a concrete value. Let's say we let n be 8. All right, then I'm going to divide this interval here into 8 pieces. Right, it's going to look like this. I want you to think about what the x coordinates, the x values of these dashes are, because those are going to be the right endpoints of my rectangles. Okay, well, what would they be? The first one would be -2 plus, what's the size of my interval? Well, I have 8 intervals, and the width is 4. So delta x would be 4 divided by 8. That's 1/2. So this first right-hand endpoint here would be -2 plus 1/2. Okay, then how can I get to my next one? Well, I would take this endpoint and add another 1/2 to it. So this would be -2 plus 2/2. This point will be -2 plus another 1/2. That's 3/2. Okay, you see how this works, right? This is just the number of the interval k, right? K times delta. All right, so now let's go back to doing this with n, right? My delta x is now 4 over n. So x star sub k is going to be -2 plus 4k over n. All right, so those are the numbers that I'm going to put into the function. Okay, so what is my Riemann sum then? My Riemann sum is the sum k equals 1 to n of f of -2 plus 4k over n times delta x, which is 4 over n. Okay, well, let's see. So what is this? This is the sum k equals 1 to n. I'm going to take -2 plus 4k over n and put it into my formula. Right? This becomes -2 plus 4k over n squared plus 4 times 4 over n. All right, so now I've got some algebra to do. Right? If I multiply this out, this becomes the sum k equals 1 to n of negative 4 minus 16k over n plus 16k squared over n squared plus 4. Still times, don't lose track of that 4 over n. It's easy to lose track of it since we're not changing it. All right, now what happens? Now I have to distribute the minus sign. This is the sum k equals 1 to n of minus 4 plus 16k over n plus 16, well, sorry, I lost it there. Distributing that minus sign, minus 16k squared over n squared plus 4 times 4 over n. Now, good things happen. The minus 4 and the 4, they cancel, right? And let's see, what's left? I'm going to factor a little bit here. Look, factor a 16 out of this middle part, right? And remember our summation rules, I can bring that 16 out in front. So this is 16 times, look, I'm also going to bring this 4 out, right? So this is 16 times 4 sum k equals 1 to n of, and let's distribute that n, this n right here, into the parentheses. 16k over n squared. Well, sorry, I factored out the 16, didn't I? So it's just k over n squared minus 16k squared over n cubed. Okay, now, here's the part you have to be thinking about for a second. Remember, n is a constant, right? The only thing that's changing here is k, as it goes 1, 2, 3, 4, up to n, whatever it is. So this is the point where I'm going to use my formulas. You know what? Let me make this a little clearer. Let's split this up. This is 64 times the sum k equals 1 to n of k, and because that n squared doesn't depend on k, I can bring it out. This is 1 over n squared. Minus, and I'm going to do the same thing here. This is 1 over n cubed, sum, whoops, see I put that 16 in there, that got factored out. Sum of k squared, k equals 1 to n. Now, bring out our formulas. We have a formula for the sum k equals 1 to n of k. I'm going to leave the 64, leave the 1 over n squared. This is n times n plus 1 over 2 minus 1 over n cubed, and this is the sum of the first k squared, right? The first n squares. The formula for that is n times n plus 1 times 2n plus 1 over 6, and that's it. Close the parentheses. Okay. Now, unfortunately, I'm seriously running out of room. So, but fortunately, we're almost there. First, let me label this. Let me call this A sub R. Okay, that is the right-hand approximation. Right, the approximation using right-hand endpoints. Now, here's what I'm going to do. Let's simplify this just a little bit further. I can cancel this one of these ends with this one. So A R equals, leave a little space here. I'm going to put something in there in just a minute. Right, this is 64 times n plus 1 over 2n minus, look, I can simplify a little here too. Cancel this one, right? And that's going to leave a 2. So this is n plus 1 times 2n plus 1 over 6n squared. Okay, here comes the magic step. Here comes, and our calculus problems are so like this. We've done like 10 lines of algebra. I'm going to do one line of calculus right at the end, and it's going to give me the final answer. Right? How do I get to the area? The exact area. Well, what I do is I take the limit as n approaches infinity. Right? Let the number of partitions get infinitely large, if you will, which means delta x gets infinitely small. And now look, take the limit over here. This is the limit n approaches infinity. All right, well, let that 64 float out here. What's the limit of this as n approaches infinity? Well, we know how to do that now, right? We know how to do that from back when we're talking about limits. This is 1/2. What is the limit of this part as n approaches infinity? Well, you notice that if you multiply this out, this is 2n squared plus some smaller terms. So because the degree of the numerator and the degree of the denominator are the same, this is just it's 2/6, which is 1/3. 1/2 minus 1/3, that's 1/6. And if you reduce the fraction here, this is 32 thirds. That is my exact area. Right? The exact area under that, between that parabola and the x-axis, between -2 and 2, is 32 thirds. So this brings us to our definition for the area of the region under the graph of a function. First, as we have so much of the class, we're talking about a continuous function, right? I'm going to define the area of the region under the graph of a continuous function to be the limit of the sum of the areas of the approximating rectangles. And that's what this is saying. Now, I've phrased this in terms of R sub n, the right-hand rectangles, the right-hand Riemann sum. If you do it with the left-hand Riemann sum, you get the same thing. In fact, we can go even further than that. We can show, this is a proof I'm not going to make you endure. But we can actually show that you can pick any point in the interval. Left, right, midpoint, mix them up, alternate left and right, however you like, and you will still get the same limit, assuming that it exists. Right? So this is going to be our definition. Now, that calculation we did here, finding the Riemann sum, formulas for the summations, taking the limit, not a lot of fun. I mean, just being honest about it. But you know, I want you to think back. Our definition of the derivative was not the most pleasant thing you probably ever had to work with. So we're kind of in the same boat now, and we're going to do the same thing for the next several lectures. We're going to take this definition that we were kind of didn't have a lot of choice about. Right, we already know formulas for the area of a rectangle, and our approximations are found by summing up the rectangles. We didn't have a lot of choice here. Just like we didn't have a lot of choice with the derivative. We were constrained by what we already knew about slopes of tangent lines. Well, we're going to do the same thing here that we did with the derivative. Now that we have this definition, we're going to go in search of easier ways, better ways, to calculate these infinite sums for specific functions.